Okay, hello everyone. So welcome to the seminar time. Okay, this time the topic today is the symmetry, right? And then I will go into a little bit of group theory, right? So it's more advanced in mathematics, but something that's not so hard to know, right? And so we're okay. So we talk about symmetry. Now let's look at the square. This is a square. So how many lines of symmetry do we have? 4, 8, right? Lines of symmetry, okay? So you say 8, okay, 4. Let's see, so what's a line of symmetry, right? So it's kind of reflection. You have a mirror, yeah, you have a mirror somewhere, and then the two sides are the mirror image. So some people say 4, some people say 8. Let's see. Let me try to draw it. Okay, let me try to draw it. So one is horizontal. One is horizontal. Okay, so this one I have a center in here. So let me actually move the one to the center. So that's a horizontal line. And then there is a vertical line. Okay. There is a vertical line. That's a line of symmetry as well. So not quite accurate. Okay, so let's just let's say it's, as long as it's good enough. Okay, so that's a second one. And then so Nathan is saying to me that a line of symmetry makes it so the shape is flipped around, it looks the same. Yes, okay, so that's exactly right. So what's symmetry? So Jerry said it's 7. All right, so well, some picture will have 7 symmetry. It's only 4, right? So okay, so let me draw all the 4, and then yeah, it's a diagonals and the other diagonal. So that's just 4, right? Just 4. You go 8 directions. You go on 8 directions. That's fine, but that's 4 lines. 4 lines. Okay, 1 horizontal, 1 vertical, and 2 diagonals. That's right. All right, so good. It's 4. So the square has 4 lines of symmetry. So that means we could actually flip 4 different ways, and it's going to be the same as before, right? So that's a simple. Okay, let me clear that, and then let's look at the next. Okay, regular pentagon. Regular pentagon. How many lines of symmetry? 5. You guys sure it's 5? Okay, 5. Yeah, okay. So it's let's draw the 5. Okay, so 1 is the vertical. Okay, so I have the center here, so just connect the center, and that's a line of symmetry, no problem. And then we could do that line of symmetry, and this direction. Oops, I need to move it a little bit. Okay, so this direction, and the remaining 2 are like that. And finally, this. That sounds good. Move a little bit. All right, so yeah, so our focus is on symmetry, right? So on symmetry, so that's 5 lines of symmetry. Okay, so we could actually flip. Okay, so flip is a flip along across any of these lines, and the result is still the same. All right, so let's see another one. Let's see another one. You guys tell me. So how many lines of symmetries are these? So how many different lines of symmetry? 9? So this is, yes, this is actually a regular nonagon. So that's 9 sides and 9 vertices. So you guys all say 9, right? Okay, yeah, that's right. So it's 9. So actually what we could do is to connect one vertex and the center, and then extend that. to the line. So that is one line of symmetry. We could do any of those, right? So that's just okay. So yeah. So you see that if it's a regular polygon, if the number of vertices is the same as number of symmetry, number of lines of symmetry. Okay. So yeah, we do the reflection like that. So it's not odd number. It's for the odd number, we just connect the vertex and the center and the extent. For the even numbers, it's not enough because you, like the square, you connect vertex like the square, right? The square is like you connect the vertex and then you actually get the same, as you connect the other vertex. But the good thing is you can connect the midpoint of the opposite sides, and then that's another one. Okay, so that's for the even number. So at the end, everything is the same number of symmetry as the number of vertices. So that's simple. Those are simple things. So let's actually consider something. Okay, so there's also another type of so-called symmetry. Okay, so this is called a rotational symmetry. So it's basically you do a rotation, and around the center. Okay, you do a rotation around the center, and still the result is the same as the original one. So I put these two things here. I want to actually label. I want to label the vertices. So for example, I say ABCD like this. ABCD, that's the original. ABCD. So if I rotate the whole thing around the center by 90 degrees, or counterclockwise, right? So I'm gonna do this. 90 degrees, right? So what's gonna happen to A? A is going to here, and then B is gonna here. So you see the blue vertices. I'm doing the marking the blue vertices. Okay, so C is here, D is here. That is also an operation. Okay, so that's a rotation. That's a rotation. Okay, so we do 90-degree rotation. We get this from the left to right, and the shape is still the same square. Okay, so that's a rotation. That's a rotation. And you could do more rotations. Okay, so counterclockwise. Right, so counterclockwise. So we could do another rotation. Okay, so from the original to this 180 degrees. 180 degrees. So what it means on the right hand side is that the A becomes the other A here, right? And the B becomes this. C is here and D is here. So every vertex becomes the opposite. All right, we can say this is a reflection along the BD. That's fine. Okay, that's not quite true. Okay, this is not quite true. So this is not reflection. This is rotation. This is rotation, 180 degrees. Rotation of 180 degrees. So that's the another rotation. So we could do even more than that on rotations. Okay, so we can do another 90 degrees. So this whole thing is a 270 degrees. So in that case, what's going to happen to the vertices, right? So I'm just going to label the vertices, and then we have A is here, B is here, C is here, and D is here. That's the result of 270 degrees. Okay, so can we do more? We could definitely do more. We could definitely do more. Okay, so there's rotate 90 degrees more, so that's a whole circle is 360 degrees. But that's what? That's going to give us the original. All right, so everybody return to his original position. Okay, so that's, we can say this is four 90-degree rotations. That's fine, but it's back to the original. Okay, so that's a kind of a rotation. That's kind of, yeah. So the rotation, there are 4 different kinds of rotations, right? So after that, it just repeats. One is that we don't really do anything, just stay right there. It's the same as we do a 360-degree rotation. Okay, so that's also pretty simple. And also another simple case is reflection, right? The reflection is that we talk about the symmetry, line of symmetry. We just focus on the squares. Let's just focus on squares, and then we have 4 lines of symmetry. So if you really reflect along one of the lines, so A, B, C, D, that was the original situation. If you actually reflect on the vertical line, reflect across the vertical line, okay? So what do we get? Actually D is here, C is here, A is here, and B is here. So is this the same as any of the previous ones that I was mentioning? That any of the previous one that we did for rotation? So no, so it's new, right? It's not the same. The reflection across this line is not the same, right? So okay, so that's true. Okay, so we do reflection across the horizontal line. It's like this. It's like this. It's not the same actually. You look at ABCD, the 4 letters. It's a clockwise this time. Right? So ABCD originally I marked them as a counterclockwise direction. But then the new one is clockwise. These two are not, you cannot make them the same. You cannot do a rotation to make them the same. So reflection is different from rotation. Right, so, okay, yeah, that's fine. We just started talking about the rotation and reflection and those kind of stuff, okay? Okay, so let's look at, okay, let's see, we're having another reflection. Okay, let me erase this and then make it horizontal line, and wait, okay, so yeah, so reflect horizontal. Okay, let's see. ABCD is like this. And then if we reflect this, it's gonna be A here and B here. And the C and D are also exchanged. Okay, so this, if you look carefully, this also not any of the previous one. Okay, rotate any of the previous one, it doesn't work. Okay, so that's the that's the thing. So it cannot be reached by rotation. Okay, so this time it's clockwise also. Yeah, it's clockwise. Right. So yeah. So you can see after rotation, after reflection, the order of ABCD from counterclockwise it becomes clockwise. Can we try another? Let me try another rotation. Okay. No, reflection. Let me try another reflection. So this time, I'm going to take AC and take this line and we'll reflect across this line and see what kind of things we have. Okay, so this time is AC doesn't change because they're on the line of rotation, and B and D are switched. Okay, look at that. It's also ABCD, the 4 letters, also in a clockwise direction. Right? So you know after one reflection, counterclockwise become clockwise. So this way you can never rotate this thing from from a counterclockwise to a clockwise direction. Right? So that's a thing here. Now let's move forward and think about these operations. Okay. So the operation we can define these transformations, rotation and reflection. Okay. So here is identity means we don't really do anything. I call it I. Okay. So if you don't do anything, that's we call it transformation, but it doesn't transform anything. Okay. So that's we can give it that if we do nothing. Okay. So if you do the rotation, I can do R1. It's counterclockwise by 90 degrees. That's one rotation. And R2 is counterclockwise 180 degrees. R3 is 270 degrees. And R-1 is 90 degrees clockwise. We could do rotation, the clockwise rotation, right? So I can also define R-2, R-3, right? Those can all be defined, okay? So I can also say R4. Okay, think about R4. By this pattern, okay, 90, 180, 270, R4 is like 360 degrees. But think about this, R4 is just the same as I, the identity, okay? So it's not gonna do anything. And R4 is just back to original. So those are the transformations, the kind of actions we take, and every action we give it a name. Okay, call it a rotation or call it reflection the next. Okay, reflection. So the reflection is a FH flip horizontally from left to right, right to left. Okay, so flip horizontally. So and F of V is a flip vertically. So I don't want to use R because I already used the rotation for R. So reflection I use flip. Okay, so same thing, flip. Okay, so okay. So let's see if we do this twice, F the flip twice, right? Think about this. If we do this flip twice, flip one time and then horizontal flip another time, what are we gonna get? You just get back to original, right? So we get this identity. We get that identity. Yeah, very good. Okay, so very good. So same thing for the vertical. We get that identity. Okay, so now let's see if I actually do. Let me see if I have the next slides talking about this. Yeah. Okay. So let me talk about this. Okay. So let me go to this page and talk about this. So now I'm actually making combine the transformations. It's called composition. So what's composition? I do this first and then do this next. Continue to do this. We do a rotation once and we do another rotation. So that means R1 is 90 degrees. And then I do another R1, another I1, 90 degrees. So it's a combined result is R2. It's a right. So, okay, last one is true. Okay, that's not there yet. Okay, so R1 and R2, so basically add up the degrees. So we get R3, the 270, right? So let's look at this. What is this? R3 and R2 combined. We do R3 270 degrees and R2 is like 180 degrees. So what is this combined? We get back to R1. You sure? Does everyone agree with that? We get back to R1. Okay, does everyone agree? So let's see. I think I have another page to do this. Okay, so let's actually try this. Okay, just experiment. Okay, experiment. It's better to do the labels. Okay, A, B, C, D, and then we're gonna do 300. So so yeah, I'm not there yet, David. Okay, so I'm gonna have that question. So this current question is R3 combined with R2, right? So first I do a 270 degree. So A becomes this, and the B is here, and C is here, and D here. So now I do another, do a R2. So A becomes here, and B becomes here, and C is here, and D is here. So you see that's the same as R1. Right, so that's true. And then let me go back to the previous page, okay? So tell me about this, R1 and R91. Not back to the identity, okay? R1, so R91 is canceled out. So one is 90 degrees counterclockwise, one is 90 degrees clockwise. So they cancel out, okay? They cancel out. So how about these? These are, we just said, these actually cancel each other out. So this is I, and the vertical flip is also I. And this one is R1, and this one is I. Okay, so that's good. So is this true? Look like someone already answered this is true. right? So 270 degrees counterclockwise and 90-degree clockwise. It's the same. It's the same. Good. It's the same. Yeah. So and also now let's see what David's question. FH, the horizontal flip combined with the vertical flip. All right, so in that case, let's also go to the picture. Okay, go to the picture. Let me erase the ones we don't need. Right, erase the ones we don't need, but we will flip twice. We'll flip twice. So first of all, flip horizontally, and then we're going to have a here and a D. No, it's actually A and D switched. A and D switched. Right? So A here and D here and C here and B here, no problem. So then we do this vertical flip, right? Vertical flip is D becomes here and C becomes here, and the B is here and A is here. So you notice that we actually back to counterclockwise, right? So if you ABCD is a counterclockwise to begin with, you do one flip, it's clockwise. You do another flip, it's counterclockwise. Right? So it doesn't matter which flip you do. Right? So you could horizontal flip and vertical flip, or you could diagonal. I didn't put the diagonal, I just put these two. Okay, so I just put these two. And yeah, so let's not worry about the diagonal flip. Right? Just put these two, horizontal, vertical. So these combined, these two combined, it's back to counterclockwise. And then compare with the original case, it's actually rotated 180 degrees. So it is equal to R2. Right, it's equal to R2, right? So, okay, so think about this combination of these things, okay? Because next, we're going into something that's into abstract algebra. Just relate to this, we talk about some kind of these kind of objects. We are combining them. We are actually doing the composition. This is called the composition of transformations, right? So let's go into these. Okay, so compare these operations with multiplication, right? So think about the multiplication, two numbers. A times A is A squared. A times A squared is A cubed, right? And A times A to the -1, that's 1 over A, reciprocal, right? So n equal to 1, and so on. So these kind of things are the multiplication. So this is actually very similar to what we say about R1, right? R1 is just A. R1, and we combine with R1, we get R2. Right? R2 is actually, we can say this is a square of R1, or the R1 composed with itself. So this composition is not quite the multiplication here, but we can say the result of this operation is like do this twice and we get this one. And then if you keep doing it, after you do the R2, you do another R1, okay? So then you get R3, and so on, okay? So of course, the normal multiplication, it doesn't go back to 1. It doesn't give you the square, the fourth power equals 1. But that's okay. That's something we compare. Okay, so something in the actual numbers, we can also have this. You know, someone may mention, okay, what about modular arithmetic? Okay, modular arithmetic, you do the remainders. But that's true. Okay, remainder, when you do remainders, you actually get back to cycles. But the normal multiplication, it doesn't have cycles, but we do have these kind of reciprocals. In this case, we have the R1 and the R91 get back to the identity. That work like a reciprocal. And this identity, why do I call this identity? Because if you actually combine this R1 with identity, what you get is the R1. Identity is what? You don't do anything, right? You don't do anything. So you do R1 and then not anything, of course it's R1. And then it's the same the other way around. You first say, I don't do anything. And then the next step I do R1. So of course you get R1, right? So that's those kind of things. It means this is so-called identity, okay? So similar to the multiplication, the number 1 1 times A is 1, right? And A times 1 is also 1. Okay, and also there's another thing. So like this, A times A squared is A cubed. If I switch these two, I do the R2 first and then do R1 first. Do I still get R3? Guys, are you paying attention? Okay, yes, yeah, of course. Okay, we're adding up the angles, right? So this 90 degrees and 180 degrees, does it really matter which one I do first, right? So it's kind of addition. So this is also true. So you switch this, you get the same result, right? You switch any of these, you get the same result. No problem, right? So that's no problem. Let's actually think about more, right? More abstract situation. So the multiplications have these properties. You switch them, the result is the same, right? A times B and B times A, same, right? And associative relation, okay? So this is associative property. So if you have 3 things, you do the first two first, and then you do the then do the third one, or you actually combine. You actually multiply the second and third first, and then you multiply the first. Doesn't matter. It's the same, right? It is the same. So that means this is associative. Okay, it's associative property, and especially in the normal multiplication, it doesn't matter you switch them or it doesn't matter you combine them in any way. So you can basically do whatever you want. You can switch around the stuff. So that's why we have some method of quick multiplication. For example, I say 496, and then I'm multiplying the number 8 first, and then after that I multiply number 125. In that case, you say, okay, I don't want to do this first. I want to pick the 8 and the 125. I know this is 1000. Then the result is 496 with 3 zeros at the end. You do that in 1 second, right? You without multiplying this. If you really want to carry out this multiplication, it takes some time, right? But you recognize these two get to 1000, you just get 1 second to get the result, right? So that kind of thing, because of these properties, right? That kind of thing will work, right? So okay, so let's look at the more general, and also this is very important. A set of positive integer is closed under multiplication. What do you mean closed? It's just that if you take 2 positive integer and then you multiply them, you still get a positive integer, right? You don't get anything outside this field of positive integer, right? So it's closed under that multiplication, okay? So it's not closed under division. Positive integers, if you do a division, you sometimes still get a positive integer. So 6 divided by 2 is 3. That's still okay, but not everything, right? So for example, you say 6 divided by 4. Okay, so that's not, okay? So what is it? So that's not a positive integer anymore, right? So no longer positive integer. So that's not closed. So this division is not closed. But multiplication is closed. And we can also say addition is closed, right? So under addition. So that set is closed under multiplication and closed under addition. So you see what we're talking about is actually 2 things. One is the set itself, the positive integer. Another thing is the operation. The operation is also important in this property, right? So we say, yeah, so the operation of multiplication with a set of this is, first of all, it's closed. So that means any 2 numbers multiply is still in the set. Another one is associative, and then it's commutative. Those are all basic properties of this, right? So then we go in here, we just take those kind of properties. We don't really care about what is actually is. So is it multiplication? Is it addition? They have the same property, right? So then let's talk about this set of rotations. Let's not worry about reflection yet. Rotation, okay? So so here is it closed under composition, right? So we talk about rotation. We have 4 different rotations. I is one. The identity is you don't change, you don't rotate anything. 0 degrees. or 360 degrees, same thing, okay? So R1 is 90 degrees, R2 is 180 degrees, R3 is 270 degrees, and then the R4 is the same as the I, right? So then only these 4 items. Is this close under composition? Is it yes or no? Just answer yes or no. Yes, right? It is close because yeah, you combine any 2 of them, you go back to this. Yeah, we're doing kind of a rotational. Yeah, this is kind of a modular arithmetic. Okay, so close. And then is it commutative? That just means if you take any 2 of these, you switch order. Do you get the same answer? Yes. Okay, we're adding up the 90 degrees, multiple 90 degrees, no problem. Is it associative? Yes or no? Okay, yes or no? Yes, it's still yes. Okay, so associative is still yes. Just remember, if you do R1 combined with R1 combined with R3, you could do this. Okay, so you do these 2 first, you get a R2, right? So that's 180 degrees, and then you do another R3 is 270 degrees. You add them up, you actually get back to R1, right? So if you do this, R1 and R3 put together is 360 degrees. That's I. And then you multiply by, or you just say compose by R1, it's still R1. So this is R1, no matter how you do it, right? So the rotation themselves, it's yes, okay? It's associative. Now let's look at the inverse. Inverse means, do we have a solution to this equation? Right, so let's go back to the multiplication case, right? The multiplication case, I forgot to mention the inverse, right? So the multiplication case is the positive integer is the inverse. Is there an inverse? Well, there's no inverse, okay? So the inverse means is there a solution? So given an a times x equals 1. 1 is the identity, okay? Is there an x? Is there a solution? Always a solution. When a equals 1, there is a solution 1. But if a is not 1 in positive integers, there is no solution. So it doesn't have an inverse. So positive integers doesn't have an inverse in multiplication. But if I say real numbers, the real numbers, positive real numbers in multiplication, do we have an inverse, right? Is there an inverse to this? If I say a is any real number, positive real number, times x equals 1, do we have a solution? Yes, we do have a solution, right? So we do have a solution that's 1 over a, the reciprocal of a. So that's, this set has an inverse, right? So this set and multiplication has an inverse. So so yeah, let's go back to the next page. So for this rotation situation, R1. So is there inverse to R1? R1 times some kind of rotation composed with any some kind of rotation is identity. Do we have one? We get R3, right? We get R3. Also, we have the R-1, right? So R-1 is the same as R3. We said that, okay? So that's actually R3. So that's a inverse. R1 and R3 are inverse, right? So also R2. R2 and R2 itself is inverse. So yes, is for every rotation, there is inverse. How about inverse to I? What is the identity inverse? It's just I itself, okay? So this is true. Every element has an inverse. Okay, so that's actually pretty good, okay? Pretty good set and pretty good structure. So this kind of structure, okay? This kind of structure, we get a name. All right, so let's also talk about reflections, right? Reflection. So is it close under composition? So reflection only contains, I only talk about the identity, and the reflection is F, H, F, and V. Okay, so only the three. So let's see, is it close under composition? If you actually do, is it actually do this F of H and F of V, is it closed? Well, hard to say that, right? So if I actually compose this, we just mentioned this is not a reflection. This part is actually equal to R2, but we're not including that. We just say reflections. So this is not closed. This is not closed. Okay. So it's something outside. So this is not quite the same, right? Not quite the same. So, but let's overlook that one and then say we know the result, right? It's not closed under a composition, but we know the result. Can we say it's commutative? Is it commutative, right? So say we have two operations, we switch them. Is it the same? Look like it's the same, right? So of course these opposite operate on themselves. It's no problem. That's a commutative, of course. And I, no problem. It's just these two. Just these two. If you do this, switch the order, it's still R2. So that's still commutative. So this is yes. Is this associative? Okay. Is this associative? That's a hard one. That's a challenging one, right? So let's see. If we have a f of h, okay, so reflect on that, and then we have fv. So if we do the first two, so this one becomes I, so this one becomes fv, right? So flip over the vertical, right? So the flip the same, you just do the same flip twice, then it's identity. Okay, so then you do this is this. How about we change the order. Do these two first. Do these two first. We get R2. We get R2. So the vertical reflection, and we work on R2. Are we going to get to FV as well? So horizontal reflection, and then do an R2 rotation and 180 rotation. Is it the same as this? So you say yes. You sure? Think about it more carefully. Okay, think about it carefully, and then convince yourself it is true, right? So if not, let's go back to the picture and see if we can actually make it happen. Okay. So the picture is this. I still label ABCD to make it easier. ABCD. And here, if we do a horizontal flip first, no, we're doing this part first. Horizontal flip, right? And then vertical flip. So we're going to get R2, right? So everybody becomes this diagonal opposite, A, B, C, and D. Now let's do a horizontal. Actually, we want to do the horizontal flip first, and then we want to do the R2 next. Okay, so let's do the horizontal flip first, and then do the R2. R2 is like everybody switch with its diagonal points, right? So let's do the FH first. So this means we have A here and a B here, and then we have D. Wait. A. Oh, okay, I'm getting confused. Let me use red to label them. So horizontal A here and a D here, and B here and a C here. Okay, and then we are going to combine this one is R2, right? So we're going to do R2. R2 is switch the diagonals, C here and A here, and then D here and a B here. So this is actually the vertical flip. That's actually true. Okay, this is actually true, vertical flip. So it's true, right? So it is associative. I have to go to that page. Okay, so set of reflection. It is associative. Now the last question, I erase everything, right? Is there an inverse to every reflection? So, well, that's easy. That's easy part because we know the reflection. We know the reflection inverse to the reflection. Okay, so the inverse of any reflection is just itself. Right, you reflect over horizontally and then you just reflect back. Good. Okay, that's back to identity. So that's inverse. No problem. The problem here is it's not closed. It's not closed. You see, we actually generated some extra elements like R2. Right, so in that case, this set itself is now closed. So a lot of these are hard to say, right? So hard to talk about, especially when we try to look at associative community, right? So, okay, so then we put some requirements for the algebraic structure. It's not like an algebra, we're doing operations, but the elements we're doing operations, actually those themselves are transformations. Okay, those are, we think about them as some abstract object. But they are not the real object like squares or like the points or something or lines. They are the actions. We can put those actions as items, as elements. So I'm going to go into the abstract definition. A group. So what's a group? It's not like our groups, okay? So like in summer camp, we have a group of the red group, green group, blue group. We're grouping, putting people together as a group. In this case, it's not just a set of people, set of items. We still have to have an operation. Okay, I do the small circle to indicate the operation because in the normal case, we can have a multiplication, we can have addition, subtraction, and then we can raise to power, and then all different kinds of operations. And this binary operation, we have two things, and we have a result. Okay, so those are the operations. So first of all, requirement is has to be closed under that operation. So if two elements are in that set, the result should be in that set as well. That requirement is very important. Okay, so it has to be closed, and then it has to be associative. We want it to be associative. Notice that we don't require commutative, right? We don't require that AB equals BA. We require that the associative. So, and also we need identity element, right? Just multiplication, we need one. We need number one. So you actually multiply one onto this, each thing you get the number itself. For everybody, you have to have identity. And then also we need inverse, right? So inverse is like you multiply them, you get the identity. So as long as these four conditions are satisfied, this is called a group. Okay, so that's the algebraic group, right? So the mathematical concept of a group. Okay, so why do we need that? Okay, why do we need this? You see this one based on the operation, based on the symmetry and the reflection and rotation, those kind of things. It's kind of the essence of those things. We take it out. And then also get the examples like a multiplication and addition, similar, okay, addition, and so on. So those things have the same essence here. So we want to take those out and see what are so fundamental about them. So that's the identity. But you see, what's the use of it? In fact, in the history, at the beginning of this, it's not many people see the use, or not many people even understand this. All right, so let's see who invented these things. Okay, so that's this guy. Okay, Galois. Okay, so this picture actually he's a 15-year-old, a portrait 15-year-old, right? Yeah. So right, so that's what happened. So when he was teenage, he was reading the mathematical textbooks like reading novels. Okay, so that was a super genius kind of person, and then he actually invented this term called a group, and of course I think the concept of this, the abstract concept of this algebraic structure. I guess it's not invented by him, but he used the term group. And he developed the Galois theory and the group theory. So this Galois theory is still what we learn in college. Okay, so very hard and very hard to understand. So at his time, he actually talked with the time's greatest mathematicians, like Cauchy. Okay, I'm sure many of you heard of Cauchy. And also Poisson, okay, Poisson. So those people are famous mathematicians in history, but they could not understand his paper, his writing. Well, I think Koji understood. Koji noticed the importance of his work, but somehow they didn't work out. Okay, so the thing didn't work out. Okay, so then he actually found out what kind of a polynomial are solvable by radicals. We know that the quadratic polynomial can always be done by radicals. Okay, so the other things like cubics and the quartic and all those things, at the time when he was alive, it's actually those things are already solved. Okay, so the quartics is solved, and people try to solve the degree 5, and nobody actually came up with a general solution. And then he proved that degree 5 there's no general solution. Okay, and also someone at his same time, very young, also very young, named Abel. And he was, okay, so if he was so smart, why would he do, okay, so yeah, so that's a good question, okay? So Abel was also very young, a little older than Galois. And then he also developed this similar theory, and then unfortunately, they didn't meet. So Abel also developed this kind of a theory, and both of them laid down the foundation of this abstract algebra, and then they proved that the polynomial degree 5 or above, they don't have a general radical solution, right? So okay, so let's talk about this. He was actually involved in politics. Okay, so all those political things during that time, you know, in France, there are a lot of these. You know, the support the king or whatever. So he was in politics. He was pretty radical, and then he was arrested and so on. And then what happened is someone actually talked him into a duel, and then about a woman involved. So so exactly what happened is still a lot of people have different stories. Okay, so then. But anyway, he was in a duel, and then he knew that he couldn't win. He knew he couldn't win, and before the day of the duel, he actually spent a lot of time to write down all his mathematical ideas. Right, and then on his paper he said, "I have no time. I have no time. I'm gonna die. I'm gonna die in the morning." And yeah, so he just said that. He just wrote that and a lot of pages. And then the next day, he actually went to so they use guns, right? So he got shot on the abdomen, okay? So, and then he died later. He died. And his brother later on, after he died, his brother tried a lot of years to try to publish his papers. And eventually people recognized how important his math is. And then okay, so he's one of the super genius in history, mathematical super genius, and yeah, unfortunately, those super genius, the life was short. So their life was short. Okay, so sometimes in college we say, okay, so what if they live longer? Then we probably have more difficult mathematics to learn. Okay, so that's a kind of thing. Okay, so let's go on with the theory, okay? So now, question, are these groups, based on the definition, are these groups? First of all, the 4 conditions, okay? First of all, is it closed? Is it real number, R is real number. The real number with a plus sign. Okay, so with a plus operation. So say the real numbers, are they closed under addition? Yes, right? Are they, is it associative? Yes. We don't check commutative, okay? We just check associative, yes. And then there identity. Identity, what is the identity for addition? It's 0, yes, it's 0. 0 add plus anyone is the same as a number. 0 is identity. Does everybody has the inverse? Yes, so plus or minus. So positive number, negative number. So yeah, this is a group. Now let's look at positive real numbers and multiplication. I should say positive, okay, with multiplication. So positive, do they have, okay, does it have a, okay, is it close? Yes. And then, so associative, yes. Identity for multiplication is 1, right? 1 times anything is that number. And then is there inverse? Inverse means reciprocal, yes. So this is group, okay? This is group. But if I say not positive, just real numbers without that positive, then it's no, because 0 doesn't have an inverse, right? So 0, the number 0 is not an entity. 0 has no inverse, so that's no. So let's look at addition in integers. Integers, well, this is similar to the addition with real numbers. It's actually closed, and there is associative and identity is 0, and then negative numbers. Okay, so this is yes. And how about this multiplication? Positive integer multiplication. That one, is it closed? Yes. Is associative? Yes. And identity is 1. And inverse, oops, there is no inverse for anything other than 1. Okay, so that's not a group. That's not a group. You just check these. Okay, you don't. The actual operations is actually not so important, but you need to check if this work. Okay, so that's those are clear things about groups. Okay, so and okay, come on. Okay, so I actually should say positive integer with n. Okay, so let's look at this. Now let's go back to transformation of a square. This time I put the colors on the squares. So let's see the time. Okay, oops, I almost out of time. Okay, so I put the transformations. I put the colors on these things, and then just to say what is the rotation. Right, so in this case, this is original. This is original, and then from the original to this, it's actually clockwise 90 degrees. Right, so to here is clockwise 180 degrees, and this is clockwise clockwise 270 degrees. Right, so yeah, so or you can say counterclockwise 90 degrees. Right, so that's okay. So this is R1, this is R2, and this is R3. And from here to here, it's a reflection, right? So you're flip vertically. So that's after you flip V. So this one from that to here is a flip vertically. So that means R3 composed with this, right? So I don't think we have a name here from the original, right? I don't think there is you have to express this way, okay? And then, so flip, okay, so you could say, yeah, you could say flip the line according, but I'm not talking about the diagonal flip, only the horizontal vertical, right? So then the only thing is this. So this is R2 combined with the flip, right? So, okay. And this is R1 combined with the flip, okay? So, okay. So let's see. Yeah, R was counterclockwise. That's why I say this is R1, this is R3, right? Right, so this is counterclockwise, right? So this is R2 and the counterclockwise and clockwise R2 the same. All right, so this one is this, okay? So the second one on the bottom here or here, R3 flip of this, okay? So the thing here is R3 here, and then you reflect the vertical is here, right? So now the question I'm having here is actually what I'm talking about is this whole thing as a set, this whole thing 8 positions. This is actually a group. Okay, so this 8 operations, or 8 transformation is a group. Right, so carefully think about this. It actually is anything you do in terms of rotation or the reflection horizontal vertical. We are not talking about the diagonal reflection. Okay, so horizontal vertical reflection, This is a group. This is a group. But the question here is this the group means it's closed, okay? It's closed. Think about it, it's closed, right? So any operation you do here is closed. And also what if okay. Yeah, let's see. I actually don't have time to talk about example of in the AMC, so that's okay. So I just talk about this. I just want to mention one more thing here. Is this commutative? Because yeah, the seventh one. So you mean this one is FH? Okay. All right. So my question here is this operation. This operations is a composition operation. Is this commutative in this thing? So the associative definitely true. All right, this is associative, but it is commutative. That means if I do R3 and I do a reflection here, so FV, so that's going direction to go here. So what if I do FV and R3? Is that still the same? Is that still the same? Let's think about this. It still may be the same, okay? So yeah, so maybe this is, oh, okay. So actually this is not R3, R3 FV, okay, RV, FV and R3. So, okay, so let's see. If we do RFV, FV sum means you, from the original you get this. If I do an R3, R3 means counterclockwise by 270 degrees. Do we end up here? No, we don't end up here. We actually end up here. Yeah, so you see this, you change this order. This one end up here, but this one, you actually end up there. Yeah, think carefully, okay, think carefully. This, because I put the colors there, you can see how you're gonna rotate it. R3 means you rotate 90 degrees clockwise. Okay, so reflection, FV reflection is here, and then you do a clockwise 90 degrees, you actually end up here. Okay, so that means the switched order actually you have a different result. Right, so that particular one means it's not commutative. It's not commutative. Right. So here this one probably is still, you switch them, you still end up here. That's no problem. Right. So but that different. So not commutative, and this the transformation here like this with reflection involved is not commutative. Right. So that's a thing here. Okay. So let me see the time. Okay, the time is up. So let me show you what I prepared to do next. Okay, so this actually the answer here is a group. It's associative but not commutative, and inverse exists. Okay? It is a group. Okay, it is a group. So so the next question is actually AMC 10. Okay, so that I won't have time to discuss the solutions. Okay, I'll just say this is very much involved in this the group theory scenario. Okay, so you see the question is a 10A and 12A question. Okay, number 23 on the 10A, I believe. So it's rotation of 3 rotations like R1, R2, or R3 counterclockwise, and then reflection across x-axis and y-axis. These are FV and FH. Okay, so then we are going to do, okay, so so 3 of these transformations in any combination, because there are 5 of them, any combination will return to the original position. That means which combination of 3 make it identity, right? So that's a question about that, and how many ways can we get identity based on these rotations. So if you have thought about this, actually these kind of things, this is just operation of those rotations in this structure, right? So then you can actually get the answer. You actually get the answers. How do you order these things? And keep in mind that by rotation and reflection, you cannot switch them to get the same answer, right? So that's the kind of idea, right? So, and especially the triangle is not really the same in after you do a rotation or whatever. Okay, so then you have an answer. Okay, we don't have time to talk about the actual answer, the actual solution to this. I'll just give you the answer. It's 12, right? The answer is 12. So you can figure out, or you can check out the answers. Okay, so I think that's it for today. And so we don't have time for questions either. So we will we'll continue the afternoon, continue the morning class, and then so remember to get back to your morning class link, right? So okay, that's all for the seminar, and then hope you have fun, and then yeah, so I'll see you after the class, after the break. Okay, bye bye.